then he took the remote sensing reflectance, ran it through his little inversion model, and got an A and BB estimated from RRS, and then he put the A and BB into another model and estimated the KD, and then he assumed the solar zenith angle was always 30 degrees, and he was then finally able to get the KD to plug into his number, and the solar zenith angle goes into his little gamma. And so he finally was able to say, here's what I predict for the Secchi depth, really starting with RRS versus the measured value from the database. And it's pretty darn good. And then there were these 3 outliers here of some weird thing that he discusses. But these are open ocean waters, blue, coastal, green, inland waters, little diamonds, and coastal and ocean Chinese waters and the little X's. So it's a very convincing comparison that his technique can give you a good Secchi depth starting with a remote sensing reflectance or a KD derived from a satellite. Now, what he didn't do was compare whether his values are better or worse than the Preisendorfer values. Well, the reason he couldn't do that is he didn't have the in-water beam Cs and in-water irradiances and stuff that you would need to compute the photopic quantities to evaluate Preisendorfer's equation. So anyway, there's still work to be done there, but I think he's doing some good work there. Yeah.
So the part about C, KD and C being related by 1.5, that seems to be the weakest argument in this parameterization, and particularly when you look at it's been validated, or he assumed that the solar zenith angle is 30 degrees all the time. Those seem to be sort of intimately linked to me.
Yeah.
And so I'm wondering, I mean, in hydrolite you could do a lot of simulations to figure out the relationship between KD and C and find out what, under what conditions is it 1.5.
Yeah.
That seems like that's really where.
I agree. That's probably the weak part of the argument.
Yeah.
But
so I'd like to see some sense of what is the variability in that 1.5.
yeah.
And that will totally
Yeah.
change this relationship. And so I think that that's something that really absolutely needs to be tested.
Yeah. Ken?
If you calculate the CV correctly, which from what you said, you weighted by the gradients at all the points. So you're sort of, if you did it right, you are predicting in a deep Secchi depth, the depth of maximum transmission. You're not doing a photopic by itself.
Right. Yeah, because Ken's KDs, those are the radiometric guys. They're not photometric. They're just the radiometric KD at whatever wavelength where KD is the minimum.
Right.
Yeah.
That would probably be what happened if you did all that weighting with photopic, as you keep closer to that.
Yeah, basically as you went down, down, and down in the water and kept recomputing the photopic. Yeah, I agree. And that's kind of why this works, and it's why they both generally give, if you do the hydrolite runs and put in chlorophyll of 2 or something, the Preisendorfer and the Zhongping Li values are generally pretty close, although whoever it is working on this finds out sometimes they're like a factor of 2 difference, and that tends to be when it's really, really nasty water. Yeah, Emmanuel.
I'm still wondering about the difference with the atmosphere. I mean, I don't see why the theory in the atmosphere and the ocean would be fundamentally different.
Well, it's because in the atmosphere you don't have like the blue and the red wavelengths being absorbed out when you're looking across the river here, but in the water, the blue and the red is absorbed out, just leaving something in the middle.
So I can see that affecting the spectral weighting. What I don't see it affecting is the fundamental relationship with respect to what IMPs would be important. How much scattering versus absorption would weight.
Kurt, I really thank you for the first part. That first part, because I never really paid attention to the weighting part. In the atmosphere, you just do the photopic weighting. It's more constant what the CV would be or the KDV would be, versus the ocean. It's going to vary a lot more what the CV is compared to what the deep ocean say.
I mean, the place where it comes to me is I think about fog. mean, I love your first, when you have this thing, and maybe that helps explain a lot. When you have this first slide, where you see the effect of absorption, the effect of scattering,
Yeah.
and the effect of scattering, you can see that you still see the disk. So in some respect, that supports your inside is that scattering is not that, it's just deform the edges, but you still see that the object is there. While absorption, you can't see that an object is there behind. Yet I think about fog, and fog is extremely good in scattering light and getting it out and not see anything. I mean,
But I think a lot of that is the path radius, which somehow is, because you do the subtraction and stuff to get rid of this path radius. But I think in fog, what happens, as something farther goes away, you've got all this path radius between you and the object that's sort of,
Yeah, but
that would be a case.
the assumption is the path radius is the same for both the target and the background.
at some point when it's,
Yeah.
So, I mean, the way I think about it is the theories probably agree relatively well in many water types. They will diverge the most when you get to high sediment, high concentration of sediment. If you like, in some respects, like in fog.
Okay, so I think maybe one answer to this will be when we get to the point spread function.
Can I make a
Yeah.
observation about second depth? One of the things I love to do with my students is to take a secchi disc and put plastic or mylar of different colors and glue it onto the disc, and then have them record the depth at which each color disappears to black. And so that allows you to look at the secchi depth for different colors of light, and is a really great first approximation of the spectral K. And you don't have any sensors, and you're doing citizen science. It's just a great way of being able to look at spectral.
Yeah.
basically would simplify that integration.
Yeah, really, yeah, absolutely.
Yeah. Okay, well then the final guy that, or guys that have to get their finger in the pie here are Zainefeld and Pagel. And they did a paper where they said, look, we really want some measure of underwater visibility. We want to say, if I'm a diver in the water, I can see 5 meters or 10 meters or 2 meters. So what's the best way to do that? And they said what you ought to be able to do is put a black disc out here and look at it horizontally under the water. You're looking horizontally, it gets rid of this KD business, and it's only beam C. So they do their math, they do their analysis, and they say if you've got a black target underwater and you're viewing it horizontally, that the visual range is about 4.8 times beam C, not photopic, just plain old beam C at 532 times 0.9 plus a 0.08, and that's good to plus or minus 10%. And one of the last, and it was either the last class here or the one before, Zainefeld came here. He's got his little black disc. They went off the dock, they put it in the water, and he's got a little periscope where he could stand on the dock and look in the periscope and look horizontally and then move away from it and see when the black disc disappears. And so here's the results here, pretty amazing. So he's got beam attenuation coefficient versus the visibility range, so that's when he can't see the disc anymore. And there's several different things here. So it says he's got a 20 centimeter diameter black target, and then he's using beam C at 532. That's this formula. He's got one that's using 4.8 over the photopic beam C, which is the blue lines, and then there's the green line is another little formula and another little formula. And the bottom line is there's an amazingly good relationship between simply beam C, in this case at 532, and the visibility range. So, and that works only looking horizontally, but it gives you a very good measure of, if you're a scuba diver in the water, how far can you see? That's simple. And so the Navy is really, really big on what they call diver visibility. They want to know before they drop the Navy SEALs out of the helicopter, and Yellow Sea or wherever it is to invade North Korea, they want to know, can these guys see 2 meters or 5 meters? Big deal. And so they're just interested in a quick and dirty formula. And whether it's 5 meters or 5.2 meters, who cares? It's 2 versus 5. So that's why a large part of ocean optics in the early days was driven by visibility, not by caring about phytoplankton or anything. Colin?
So if you're in different parts of the water column,
Yeah.
wouldn't you want to, I mean, it would seem that, 532 is good because most waters are green, but if you're out in the open ocean and you're down at 50 meters, wouldn't you want to use 490?
Yeah, you probably would.
Makes sense if you were sort of, I don't know, two things underwater looking to see if you could see each other like submarines,
Yeah.
right? I mean, could you,
Yeah, and to get a better answer, you have to do something fancier than this little formula. But yeah.
you don't think it would be a
Oh, well, actually, maybe your point is if you were at 50 meters and, maybe you should be using C at 488 or something, and maybe this is 0.85 or 0.95 or whatever, but yeah.
But basically, it doesn't matter where you are in the water column as long as you're looking horizontal and you're picking a wavelength that is the prevalent wavelength at that.
Yeah.
Spectral shape of C doesn't vary that much.
Right, actually, that's true.
532 and 48.
Actually, so it doesn't really matter what depth you're at, that's great.
Yeah, Emmanuel.
How does that jive with Jumping's theory?
Well, I think, Zhang Ping's main thing is all we need to know is the KD, but that's for a vertical path.
But the path back is not that different than the two paths.
Well, yeah, but see, Zhang Ping is replacing the C part with 1.5 KD. And so I think in Zhang Ping's paper, he says something like, finally, so the sentence down at the bottom somewhere that says, well, if you're looking horizontally, then yeah, you can use beam C rather than.
Doesn't explain it with any theory. It does not contrast the two theories in terms of how would the new theory would result possibly with different. I think he's saying it simply because Juan was a reviewer, and there was not a real justification as to how the two are different. Yes, the path down is different, we all agree, but the path back, I don't see how that, light coming back from a disk with a background, how is that different for the case where you do it horizontal versus you can do it vertical? And this is, again, I'm just saying for the student, this is ripe for investigation.
Yeah, there's a lot more work to be done here, starting with the beam spread function. Okay, you're going to shine your light pin here out into the water just like you did in the fish tanks the first day. And you remember that beam of light, you put a bunch of particles in the water and you could kind of see how the beam spread out. Okay, there's a thing called the beam spread function, and it's defined as follows. You've got a collimated light source, so you're just shooting light out into the water or the atmosphere, and that light, of course, comes out, and some of it's absorbed and some of it's scattered all around. And then you put a plane irradiance detector out here at some distance r, and you simply move that detector around on the surface of a sphere at distance r. And so here's an angle theta from the original beam, and you'll measure some irradiance out here. Okay, so you simply take that irradiance that you measured, you normalize it by the emitted power, and so irradiance is watts per square meter per nanometer. You're putting out a spectral power of watts per nanometer, and you get this thing with units of 1/meter squared. And that's the definition of the beam spread function. So it's a measure of the effects of all the absorption and scattering between your source and your receiver. Now remember, the volume scattering function describes each single scattering event. So it comes along here, hits a particle, scatters. That interaction is described by the volume scattering function. Comes up here, hits another particle, scatters again. That interaction is described by the volume scattering function. But then the cumulative effect of all those scatterings and whatever absorption there is being described by the beam spread function. So whereas you have IOPs that are point by point, they don't depend on how far you've gone in the water or anything. Beam spread functions kind of fold all that together and say, well, all I care about is a light source here, and I'm over here shining the beam into the water. What am I going to measure? And that you can get from knowing the source and the beam spread function. So it's a description. It takes care of absorption and multiple scattering, whereas an absorption coefficient and a volume scattering function are just like for one scattering and one absorption event. So that's the beam spread function. Now, there's a little thing in electromagnetic theory called reciprocity. And it says, look, if I shoot a photon out here and it bounces around and it goes into my detector over here, if I send a photon out of the detector in this direction, it will exactly retrace the path and go over here. And that comes from Maxwell's equations. If you just let time go to minus time, everything stays the same, just the direction of the light propagation reverses. So then you could argue, okay, I have a collimated beam coming out. I have a detector here that's a cosine response. So if I emit light in a cosine response and I have a collimated detector, I have this geometry. So notice the light ray here is the same. Whoops. And now I'm going to emit light in this cosine response and have the collimated detector. And so I'm going to measure here at angle theta, and the light's being emitted here in this cosine pattern. So then there's a little thing called the point spread function. I have a point emitter here, and I'm going to let it emit light, and I'm going to scan my radiometer back and forth past it and measure the radiance. So the emitted intensity here, so this is watts per steradian per nanometer. So it's some power over pi, and a pattern here that goes like the cosine of the off-nadir direction to the sensor. Remember, planar radiance sensors have a cosine response, so I'm going to use a cosine emission pattern. So I'm going to emit light that goes like the cosine of the angle here between 0 and pi over 2, and then it's not emitting anything to the back. And if you integrate this function here, you just get the integral of that times solid angle. That just gives you back the power. So we're going to emit intensity with that pattern, and then we're going to measure the radiance, and the point spread function is then take the measured radiance, normalize it by the power over pi, check the units, and it comes out once again meters to the minus 2. So that's the point spread function. Now, lo and behold, it turns out that, well, actually, here's to give you a little more feeling. If you're looking at a street light here, so here's a light pole, street light, you're looking at this through the fog, and it's bright here, and then it gets darker out here. That pattern of brightness is basically just the point spread function. And if it's not foggy, you get a really bright little point here, and if it's really foggy, it starts to kind of spread out. So that's qualitatively the point spread function, with the point emitter being the street light. Okay, now it turns out the point spread function and the beam spread function are numerically equal. Here's some data from a classic paper back in '77 where they've measured polar angle, so this is my little theta, and in either the beam spread or the point spread function, units of meters squared. And these were actually measured on 2 different days in the Bahamas, and one of them had the beam C was 6.8, 1 over C was 6.8 meters, and the other day it was 7, but it's not quite the same water body, but pretty close. And the distance here that their source and their sensor were apart was 19 meters. It's really clear water. And you kind of look at this and say, wow, these guys, they look pretty similar. And in fact, Gordon finally in 1994 proved that these things are exactly numerically equal. And in between 77 and 94, you know, there were fist fights at ocean optics conferences over whether or not the point spread and the beam spread function really were equal, and Gordon finally settled it. Okay, so here's just another little example. Here's 3 different phase functions. So there's Petzold, in green, and Fournier-Ferrand for sort of phytoplankton, and Fournier-Ferrand for mineral particles. So different indices of refraction. And then I have a Monte Carlo code, guess what, that computes point and beam spread functions that I just trace lots of photons for whatever phase function and such I want to use. And here's just some example values where I've normalized all the values to 1 here. But you can see if I'm not very far away, I'm 1 optical path length away, that the beam spread function or the point spread function begins looking very much like a volume scattering function. You know, it's highly peaked in the forward and, you know, a few orders of magnitude less down here. Well, that makes sense because if there's only one scattering event, then the beam spread function is describing the propagation of light for one scattering event, but that's what the volume scattering function does. So it makes sense that this guy should look like a volume scattering function. And then if I'm 10 optical path lengths away or 30, multiple scattering smears that out and it doesn't look like the VSF anymore, but you're getting all the effects at, say, 10 meters or 10 optical path lengths away of all the multiple scattering that's going on and whatever absorption there is. So that's why these things are useful, and Dr. Voss in the back has at least half a dozen papers on measuring and modeling point spread functions in the ocean. And the reason he does that is so you can figure out what an image is going to look like. So here's the deal. You've got this image here, and let's say you're looking at this point right here. Okay, so a lot of the light that you're measuring is coming from that one direction and making it through to you. But because of scattering in the water, really every point in the image can scatter light over into your path and then scatter it here. So looking at this point, you're still picking up some light that started from this point but got scattered just right to go into your direction, or this point over here got scattered just right to go into your direction. And how much of that light got scattered here? Well, that's our point spread function. So if you're in close, let's say I'm looking at this point here, the point spread function's high. So a lot of the light from here gets scattered over to right next to it, and I see it. If I'm further away, point spread function is less, and this point makes less and less contribution as I go further away. So the really fundamental key to what's called, image analysis is this. You have a scene, so let's let S of x, y, and 0 be the pattern of bright and dark values, so maybe at one wavelength, and maybe those are 0 to 255 if it's an RGB image or whatever. But you've got this pattern of bright and dark that is your, whatever you're looking at, the shark in this case. And that's seen from 0 distance or seen through a vacuum. Then when you're looking at some point x0, y0 here from a distance z, then you have a pattern of bright and dark. That's the S at that point at a distance z. Well, you think about it a while and you realize that what I'm looking at a particular point at a distance z away is the original image up close, but times the point spread function for however far it is away from here. So I wrote this as x0 minus x, y0 minus I, and distance z, because remember, beam and point spread functions depend on the distance. So the bottom line, and of course if you want to write the distance r here, that's just in Cartesian coordinates and there's some angle theta. So when you go back to here, I've written it as theta and r, but I'm just converting x, y coordinates to theta r, so I can go look up the point spread function that I've computed. So the bottom line is I can take any image, and if I know the point spread function of the medium, then I can predict what the image will look like. So if you really wanted to account for, finite size, Secchi depths, and, whatever, all the absorption, blah, 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 I think this is what you would start with. Here's my image of the Secchi depth, and here's the point spread function of the water, and I can tell you exactly what I'm going to see at every pixel in the image. And then you can worry about things, whether the Secchi depth really did disturb the ambient light field and, all of that kind of stuff. But this is the key. So this is like the holy grail of image analysis. This is where it all starts, right here, just like everything in radiative transfer theory starts with the radiative transfer equation. And the point to be made is that the point spread function completely characterizes the effect of an environment on an image, and if you know the point spread function, you can then predict what any image will look like. And to inspire you when you get home, that integrals of this form, so you've got a function of x and another function of y minus x integrated over x, so that's going to give you a function of y, and integrals of that form are called convolution integrals. And when you get home, go take a class on Fourier transforms, and these have miraculous properties when you take the Fourier transform, and then you can do everything over in this Fourier space and do all kinds of things like filter out high frequencies or low frequencies or whatever. But anyway, I'll just let you know that that's why you need to take Fourier transforms. It's not for electrical engineering, it's for ocean optics. All right, enough said. Now, for a few minutes, let me talk about Lidar and just define a few terms here. So Lidar is light detection and ranging, which is like radar, which is radio detection and ranging. Our light source is usually a laser, but it doesn't have to be. People talk about range gating, which means you send out a short pulse, typically like an order of a nanometer in length, and then you observe the return signal at sort of like 1 nanometer bends in time, or gates as they're called. And so by sending out a short pulse and, sometime later I get a little pulse back, I can figure out how far did the light go before it reflected off of something and came back. So that's the whole business of range gating, which is the key to converting, for example, the time of return to the depth of, say, a backscattering layer in the water. And there's spotlight and floodlight lidars. And spotlight lidars are usually used for bathymetry, where you're trying to fly over and you want to get the depth at lots of different little spots here. So you may have a footprint on the ocean surface that's maybe 1 meter in size. So you're going to get the depth right there. Then over here, 2 meters away, you do another flash, you get the depth here, and you build up a chart of the bottom from lots of little small footprints on the water. And then there's floodlight lidars, where you spread the beam out on purpose, so you get a large footprint that might be, say, 10 meters by 10, and then the return signal you put onto a 2D CCD array, and then each little direction is a different pixel, and you can then build up an image of the whole thing all at once. Okay, so the basic idea of bathymetric lidar is this. You fly over, airplane, satellite, whatever, you send down a pulse, and then you go beep, 1 nanosecond pulse, and then you're measuring the return signal at, say, 1 nanometer resolution. So it starts out, okay, you're going to get some backscattering from the atmosphere, so you'll have some little signal, but sooner or later the signal will hit the water surface and you'll get a big reflection, bang, so there's the water surface. Then the signal goes down in the water, maybe there's a scattering layer here, and you're getting some return, of course, just from backscattering by the water column, and of course that's being attenuated. If it's scattered here, it's going to be attenuated on the way back up, so the signal starts dropping off. But then maybe there's an object in the water, or there's a scattering layer, you get more scattering there, so all of a sudden you get a little more signal, a little beep here, and maybe it finally hits the bottom, which is probably brighter than the water column, and then that comes up, and sometimes later, bang, you'll get a big signal off the bottom. So then you say, well, I know where the surface was, I got the signal from the bottom or from the scattering layer, and so how deep was the bottom? Well, it's the speed of light in water, which is vacuum over index refraction 1.34, and the light has to go down and back in time delta t, so it's really delta t over 2 for just the depth. So very simple little formula that all I have to do is send out the pulse, measure the delta t between, say, the surface and the bottom, or the surface and the scattering layer, plug in the numbers, and if I have a 1 nanosecond pulse, that gives me roughly 20 centimeter resolution and depth. Here's a famous...
For a LiDAR, the atmospheric signal is very low? Is that just for this?
Well, it's backscattered by the atmosphere, so that's going to be something, but it's going to be small, generally.
So in theory, if you use a LiDAR on a satellite, you don't have to worry so much about it?
Well, it's not, it's that you can say where the surface is and where the bottom was. That's what matters. We don't have to do an atmospheric correction here at all. We simply want to know how long did it take the light to get from the surface down to the scattering layer. That's what I'm interested in. So we don't have to worry about atmospheric correction. We're just looking at a time difference.
The atmospheric return is less than part A.
Yeah. So this is all, there was the pulse back here, then it's coming down here. So you're getting some atmospheric return here, but I'm only interested in where this point is in time and where that point is in time. And the magnitude up and down, I don't really care about, at least for this application. Yeah. Okay. Oh, yeah.
So if you had a highly diffusing medium like fog or snow, could you use the response as a function of time to get an approximation of the number of scattering events?
Yeah, so that's a whole different game. And yeah, people do all kinds of things like that. And they use LIDARs to remote sense particle size distributions in the atmosphere and all this kind of stuff. But I'm just talking about bathymetry in fairly clear atmosphere and water. Okay, so here's a paper by, oh yeah, sorry.
How deep can you get this?
Well, you get down with most of these systems to like 5 or 6 beam attenuation links, so 1 over C. Now, when you're out there with your eye, you can get down to maybe 2 over KD or 1 over KD. These can go a lot deeper than just the eye because you're using this time dependence. So you may get back a really small signal, but as long as it gives you an identifiable bump here, you're good to go. So the rule of thumb is the eye might get you to 1 or 2 times 1 over beam C, but LIDARs will get you down to 5 or so. And then you can do some more tricks with polarization that may even push it down as far as 10. So I left all that stuff out just because there wasn't enough time. Okay, here's a cover of an Applied Optics back in '88 by Frank Hode and company. They flew an airborne LIDAR system, started in Virginia and flew offshore and out towards the Sargasso Sea. So you're going along, you're not getting, actually they're going from the Sargasso back to Virginia. So they're going along, there's nothing much to see, and then they start picking up this internal scattering layer as they get towards the coast of Virginia. And then here they're getting a lot of stuff in the water scattering, and then right here they fly over a shoal. So that's actually bottom, and this is a plume of sediment being swept off of the shoal by the outgoing tide, or maybe it was incoming. But anyway, this is internal scattering stuff in the ocean that's down at a depth of sort of like 10, 15 meters. Then the really bright stuff was the sediment plume coming off of this shoal. And at this point, W right here, here's their actual return signal. So they've had a pulse back here. They're getting this big pulse off of the water surface. Some returns. Here's the scattering layer. So that's coming off of this scattering layer in here. And then here's the pulse off of the bottom. So it was really a groundbreaking paper that said, we can really look at scattering layers in the ocean with LIDAR. And Then the reason the NASA boys wanted me to throw in a little bit about this stuff is now this is becoming a hot topic of putting LIDARs on satellites to look at scattering layers in the ocean. So that's what it's all about. Okay, here's just an example of a nautical chart. You know, you can go home, get your credit card out, buy a bathymetric LIDAR system, and go fly around in your airplane and make nautical charts. So here's one. There's a company, it used to be called Optech. They were then bought out by Teledyne. But anyway, here's a bathymetric chart up in northern Canada with, you can't read the numbers, but those are water depths made by simply flying this bathymetric LIDAR over the area and generating the chart. Here's bathymetric surveys. You look at this, here's land here, there's seabed here. You look, there's some kind of obvious structure there and kind of a rectangular grid of some sort, and you say, wow, you know, it's the sunken city of Atlantis and I found it. And you go out to validate it, and well, it turns out it was fish cages on the bottom. So it wasn't really Atlantis. But anyway, LIDAR is becoming very important in marine archaeology, where you want to fly over some clear water place like Greece, let's say, and you find all of this stuff on the bottom, sunken ships and sunken cities and, you know, so on. So very widely used. There's channel morphology. Here's land here, and then here's the bottom of these river channels at very high resolution made by this commercial bathymetric LIDAR system. You'll never get that by going out in a rowboat with a sounding line, measuring the depth, right, latitude, longitude, go over here, measure the depth. You get very fast coverage. You know, you can fly an airplane and cover, you know, many square kilometers a day and get charts like that back by the next morning, as opposed to going around in a boat with an acoustic sensor or something like that. So these are really important. Okay, here's just one other example. Floodlight LIDARs, you're looking often for something like mines in the water. So you fly the LIDAR along and you're generating an image here. And incidentally, I looked the other day, the US Navy just put out a contract to buy what they call the Airborne LIDAR Mine Detection System, AMDS. They're spending $255 million to buy 45 of these systems, and that's just the LIDAR. That doesn't count the helicopter. You have to have your own helicopter. So there's a little pod thing that's like this big around and this long, and you buy that and you just hang it on the side of your helicopter or your airplane and go fly around and look for mines. So that's $255 million. Wardell said their budget was between $3.5 and $4 million for everything that the Ocean Biology Processing Group does, bringing you, you know, data from a dozen different satellites overnight. So that puts it in perspective. Okay, when you've got one of these floodlight systems, if you're looking at something in the water that's brighter than the background, you get a bright spot. If you're range gating, of course, if your range gating is looking above the target, you don't see anything. Then you hit the target, it looks bright. But then if your range gating is looking at a depth greater than the target doesn't disappear again because it's blocking the light from getting down there and being returned, and you actually have a dark target. So the moral of the story here is you can match your reflectance to the background and disappear when you're range gated right at the target, but you can never hide from your shadow. So here's two images taken from a system called Magic Lantern. There's your mine when you're actually hitting the mine. There's the dark spot where the mine was somewhere above where the range gate was. And when you watch this on a video, as you range gate, you start at the surface and you go slice, 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 bang, bang, bang. You get a bright spot, bang, 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 dark. And you see this bright, dark, bright, dark, bright, dark, flickering on and off. It's really kind of striking. Okay, a couple of words on the LIDAR equation, just to let you know this thing exists. So what you want to do is predict the power that you're going to get back if you send out a pulse with a certain power. So you're going to transmit a pulse out here, the laser beam will go down, It'll hit the surface. It's going to go into the water. It's going to spread out according to, guess what, the beam spread function. Here's your target here, whatever, the bottom or mine or whatever. That's going to reflect some light back upward, which is then going to be attenuated back to the surface and then finally back to your sensor. So then, of course, you have not just this, but you also have the instrument optics that you have to take into account of how big is your telescope, how big is the target, how far away is it, and all these solid angles and such. And I won't go into that, but here's the idea. I'll just skip this and go to the final one. Here's this LIDAR equation, and it says I'm going to send out a power P transmitted. Then it's going to go through the atmosphere, so there's going to be some attenuation T by the atmosphere. It's going to go through the surface, more attenuation by the surface. Then there's two terms that depend on your system optics, which are the area of the receiver and the field of view that it's looking at. So just for plausibility, if I have a bigger telescope, I'm going to get back a bigger signal. If I have a bigger solid angle, I'm going to be seeing more down here. It's going to reflect more, and I'll get back a bigger signal. Okay, so that's where that comes from. Beam spread function between depth 0 and my target is going to tell me how the beam spreads out and eventually makes an irradiance down here. So I need to know the beam spread function. And I'm looking straight down, so the angle's theta, but there's the depth. Then, let's say I'm in the water. Well, this light is coming down, and part of it's backscattered exactly back to my sensor. Well, that's the volume scattering function for 180 degrees, which usually gets called beta pi, or VSF at theta equals pi. So you need to know the volume scattering function for exactly 180 degrees to tell you what the water is going to send back. And then what comes back is going to be attenuated by some K function that usually gets called something like the system K. And it's somewhere in between beam C and KU, because it's really not a horizontally extended thing. It's not a perfectly beam. It's somewhere in between, and you'd like to know that. And then if the time gate is, say, 1 nanometer, then you're looking at a layer here of 20 centimeters or so. So how thick of a layer? If it's a thicker layer, you're going to get back more light. And then it finally comes back, it's attenuated by the surface again, and then it has to go through the atmosphere again. So that's the LIDAR equation, or one form of it. And I'm just going to let it go at that. There's some numerical examples on the webbook LIDAR page, and then there's like a paragraph to discuss each of these little calculations. But if you want to predict what your LIDAR performance is going to be, you have to know beam spread function, beta pi, and a best guess at this K function. And of course, if you want to go backwards and measure this and learn about what were the optical properties of the ocean, well, you got a problem, because you're trying to retrieve 3 numbers from 1 number. So that's now a different problem we're not going to discuss. Okay, so that's it. So a number of you have asked me what my next big adventure is going to be, but before I tell you the answer, I have to show you some chairs by this fellow Hal Taylor. Now, Hal Taylor lives in rural Virginia. You go to Virginia, you go to Luray, you start driving south, you go to the very end of the road, up on the west side of Shenandoah Mountain, in what he calls his Hobbit house. This guy is the world's exalted master of making super high-end rocking chairs. Here's one you see here. There's what they look like. Here's that one's made out of cherry. Here's the one he made for His Royal Highness Prince Charles. That chair lives in Balmoral Castle, so the royal posterior can have a decent chair to sit in. Hal Taylor has this thing he calls a Storytime Rocker, where he expanded the armrest, and then you can park your little rugrats up there and read stories to them. And the royal family of Abu Dhabi has 5 of these, and other people have their own. His chairs sell for as much as $20,000 a piece. They're not cheap. But, you know, if you're a 1%er, you need $20,000 rocking chairs around the house. So it turns out, and you can see, you know, the construction on these is absolutely perfect. The design is perfect. The construction is perfect. The woods, you know, everything is just matched perfectly here. Nobody competes with Hal Taylor. So anyway, Hal occasionally takes an apprentice. And it's sort of the old world apprentice system where you live with him, you eat dinner with him, he beats you, he sends you to bed without your dinner if you make a mistake, but you learn the art of making rocking chairs. So Saturday I fly to Virginia, and Sunday I become his next apprentice. And so there's Hal. I've never met him, I've never seen one of his chairs, but they're in museums all around the world. So I'm going to start out with a piece of wood like that's English walnut, and by the end of August I hopefully will be sitting in a decent rocking chair without having to pay the $20,000. That's the main point. So anyway, that's going to be my next big adventure. And then if all goes as planned, February 7th, my wife and I and 5 others will set sail from Ushuaia, Argentina for Antarctica on a 60-foot yacht for a 28-day sea kayaking expedition along the west coast of the Antarctic Peninsula. And, you know, it's not 100% certain. We don't have a signed contract yet for this boat, the Iceberg, but my guess is probably fewer than 100 people have ever kayaked along the West Antarctic Peninsula. Maybe 150, but only 50 of them made it back. I don't know. So anyway, that's going to be my ultimate sea kayaking adventure. I sure hope it comes off okay. Here's a picture of the Iceberg. It's a 60-foot sailboat. It's got these real high-tech sails that are some way operated electronically, and it's specially constructed, ice-hardened hull for the Antarctic. And they do like 3 trips a year. They do like a month-long ski mountaineering trip where you climb mountains and do all of that, which I would do if I were 30 years younger. But then they do usually a kayaking trip and then maybe a photography trip, or sometimes they do a science support trip. So it's there for chartering. They've got our down payment, but they haven't sent the contract yet. So hopefully this is really going to happen. And I hope it's fun, because once we leave Ushuaia, we're stuck 28 days. You know, here's some photographs. Here's, you know, your basic Antarctic kayak camp. And if it's a little too cold, you grab a couple of penguins, you shove them down the bottom of your sleeping bag, warm the toes, and the next day you head on. And, you know, it's... will be just phenomenal wildlife, of course, you know, whales and all of that. This is from, you know, previous kayaking trips that they've done down there. And I'll tell you, if you want to know what bad breath is, be downwind from a whale when it comes up and spouts, because they've had a lifelong diet of seals and salmon and stuff, and they don't brush their teeth. And it will be all you can do to keep from throwing up till the wind clears it away. Okay, there's a leopard seal. One of those will probably get me. They're as big as the kayaks. If you haven't read the book Endurance, Shackleton's Incredible Voyage by Alfred Lansing, or there's now a new book by this Carolyn Alexander, this is a must-read book. It's like one of the greatest survival stories in all of history. You go get a Harvard MBA, you will read this book to see what leadership is all about. So anyway, that's where you'll find me next February. I will not be checking emails down there. So, and okay, that's it. I ran into this guy in Kathmandu. He's a sadhu, and has renounced all family and worldly ties, and he's working on achieving moksha, which is breaking this endless cycle of birth and death and rebirth that you get from reincarnation. So anyway, cool looking character. They're all very colorful, And that's the end of my story. So take 10 minutes and then you guys take over.